Okay, it is 3:30 according to my clock, so I'm going to click over to our warm up for the day. Just a sanity check. Can y'all maybe throw something in the chat? Can you hear me okay? Like, did my headphones connect? Thank you. Appreciate all of you. Oh, amazing. Okay, so I know we didn't get a chance to go over LLRBs very much on Friday last week. So the current poll everywhere asked you just some questions about it. Why don't you take just a few minutes, take a look at these trees. But since y'all can't like talk to one another, I'm gonna walk you through this and make sure that I answer any questions. So let's come back together in like 2 minutes, but go ahead and fill out the poll everywhere question in the meantime. Let me know if you have any issues with anything. Man, rude. Zoom didn't recognize Mercy and blurred her out. Yes, but she is so happy. Man, nobody loved the pandemic more than cats, I promise. Okay, so let's talk about LLRBs or left-leaning red-black trees. Oh yeah, do we have a question?
Can we get access to the slides? Because I cannot log in the poll answer from my phone.
To the like slide deck or
Yeah, the
to,
slide. Generally, when you post slides for the lecture, that's. Can you do it,
yes,
please?
sure. It
Thank
should be
you.
posted on the course website and
Okay, let me
it
check.
should be
Yeah.
posted in the ed, but let me real quick, I'm just gonna put it in the chat because we have the technology. There we go. Save you clicking
Yeah, I got it.
around.
Thank you. Yeah.
Amazing. Okay, thanks for asking. Okay, great. Okay, so let's talk about these LORBs. So left, oh, great question. Yes, I am recording this. It's going to be recorded through Zoom to the cloud. So if you want to find it on Canvas, you can go to the Zoom tab to look at Zoom recordings. And then our wonderful TA, Sonia, is going to also make sure that instead of the Panopto link, we'll link the Zoom recording on the calendar. So when in doubt, you can always go to the calendar to find everything. Okay, so left-leaning red-black trees are a further optimization on top of the traditional red-black trees, but they're actually more similar to 2-3 trees in the way that you sort of divide them up. And so here are some of the rules of how you create LLRB. So one, all new nodes are added initially with a red link. After you do any type of organization to get your left-leaning red-black tree into a valid state, all red links must be to the left. That's where the left leaning comes from in LLRB. There can be no sequential red links, and we need to maintain balance by the number of black links from root to any leaf. So they have almost the same sort of properties as a red-black tree, but instead of counting per node, we're counting per link. So these two trees, as they currently stand, are valid red-black trees. But if I am going to insert 22 into this LLRB on the left-hand side, first, I'm going to make sure that I maintain the binary search order. So I'm going to say that 22 less than 52, 22 less than 35, 22 greater than 14. So to maintain BST, the 22 will initially go here, but now we have a red leaning link, which breaks our LLRB invariant. So what's actually going to happen is a left rotation. And now this is a valid LLRB because there's still the same number of red links to any, or of black links to any node. So from the 52 to the 76, there's one link. From the 52 to the 41, there's one black link. From the 52 to the 22 or to the 14, there's one black link. So we are maintaining just by doing that little shift. It also puts our left link to the, or our red link to the left. If we look at the other tree, we can see that it is still maintaining balance, but once I add in the 67, I'm going to start up here at 61. I'm going to say that 67 needs to go to the right, but it's less than 84, so I go to the left. And then I hit 77, it needs to go to the left of that. So that's where the 67 will go. But because we have sequential red links, we are breaking our invariant. So we're going to do a right rotation, and this is our resulting tree. So now all of the trees here, minus these guys, are balanced. These are now fully balanced trees because we are only counting black links when we're counting the balance. So red links are sort of like the red black tree, ignored. Like if in the red black tree, remember we ignored the red nodes when we were counting height. It's the same thing here. We're ignoring the red links when we're counting height. Yes, exactly. So we only count black links in terms of height. So these trees here have one black link from overall root to any given leaf node. Let's pop over to the poll everywhere. Let's see. Right, there we go. And take a look at how we're doing here. So I was just asking you some things about red-black trees. So which of the following is not a requirement for a valid LLRB? Oh, I see. I see us updating our choices. Get it? Change it as you learn. So this, all red links point to that. That is a requirement. No sequential red links, that is also a requirement. And all values must follow BST ordering, that is also a requirement. So this is the one that is not a requirement. I think hopefully you can read the whole thing on your screen. Let me know if you can't. But it says the number of red links from root to node must be the same for all leaf nodes. And it's not red links, it's black links. That was the trick here. So this is the correct answer in terms of which of these is not a valid LLRB. David, you have a question.
Yeah. So on the slides, one of them had like red links on both the left and the right. Would that be invalid? So like, yeah, that part.
Yes, you're right. Good point. That needs to become a black link actually, and then we would have to do some more rebalancing. So this rotation would actually cause two rotations. Thank you for calling that out.
Okay, got it. Thank you.
Thank you. I think on your homework assignment, you only have to identify if the LLRBs are valid, and you'll get more practice with this in section this upcoming Thursday. But is there any more questions about this warm-up problem here? Okay. Here's a slide that I put in the slide deck from Friday as well, just to kind of go through that in more detail. So you can read this as well, but just to make sure that this is highlighted for you. Okay, so let's talk about some announcements. Again, reminder, Project 2 is due Thursday. Yes, this is probably going to be a busy office hours week, so make sure that you give yourself time, make plenty of use of the oh, yes, great question. So make plenty of use of office hours. Our LLOBs on the midterm, I will say that all of the things that we have learned through Friday, which does include red, black trees, 2, 3 trees, LLRBs, and tries, could appear on the midterm. But since we didn't talk about how to implement any of them, you should only have to feel comfortable with the depth that we showed you on the exercises for the midterm on Friday. No, there has not been a resolution to the audio issue from Friday because there just wasn't any audio captured. Frankly, I don't know why. So I think I posted a link to last year's lecture on the ed board under the lecture 10 questions thread, but I am also going to go back and I will try to just click through the slides myself and speak to them, and I will post that later. But if you want to watch something sooner, the lecture from last year should be on the ed board as well. Yeah, there we go. There's that. And then, of course, a reminder that there is going to be a TA review session on Wednesday, January 31st in Smith from 6:30 to 8:30 p.m. Sorry, I didn't put that on there. Does anyone have any other administrative questions? Okay, cool. All right. Let's see, where can we access Friday's lecture recording? Like I said, the lecture recording from Friday is messed up. So you can go to the old course website as posted here. So you can scroll through that and look at any of those lectures. All of the lectures from last year were eventually converted to YouTube. We'll do that this year as well. So you can click on the YouTube links from last year and watch any of the same lectures. The TA session will likely not be recorded because you have to have Panopto access in order to do that. And I doubt that's how that room was set up. So assume that the TA review session is an in-person only type of situation. But great questions. Okay, then I'm going to spend a little bit more time talking about tries. We did talk about tries on Friday, but like super briefly. And I know they are also on your exercise, so I just wanted to spend a little bit more time on them before we get into our new topic for today, which is heaps. And as a reminder, heaps are not going to be on the midterm. They will be on the final though. Okay, so tries, if you remember at the very end of lecture on Friday, I introduced you to another type of branching structure. It's called a trie, T-R-I-E, and it's what we would refer to as an n-ary tree. N meaning it can have as many, every node can have as many children as you want, n-ary instead of binary, like that. And this is because the core idea of the trie is to take any given key, and instead of treating it like an atomic blob or one particular entry, you split up the key into the sequence of characters. So you'll often see tries used with strings. That's the most common thing, but you might see it with like int values or other things where you have a sequence of repeating characters from a given set. Sorry, I don't mean to cough into the mic. So let's take a look at what a trie might look like. Here is a given trie. You can see it's got an overall root that has no particular value in it. That's sort of the get started. It's almost like a sentinel node. And then any given node in this case can have up to 26 children, one for each letter of the alphabet. This particular set has an A child. The A is colored purple, meaning that that represents a key entry into the set. So you can see here that contains of A would return true because that A is colored. But you can see that, say, a contains of just the singular value S, that would return false, just like SA would return false because that sequence ends on a white node, which means that's not a full entry. But it does let us repurpose this S and A so that SAM, SAD, SAP, and SAME can all be entries into the trie and still leverage that same SA characters without duplicating that data. And that's the real power of the trie. It's sort of that prefix matching behavior. This type of branching structure can be a little bit more complicated to navigate, and it can have worse runtimes because there's so many children, but it's just really good at this specific idea of finding matching prefixes. So if we wanted to find the longest prefix, or we wanted to find things with the same prefix, this is really the structure that you'll use. And you'll find that this comes up most often in things like autocomplete, whereas you start to type the beginning of some type of search, you get all of the possible results. And the way that they're doing that is as you type in a single character, it's navigating through branches of the trie and then returning all of the child nodes after as you type so that you can kind of get the collection that matches that path within the trie. That's, I think, as far as we got on Friday. Does anyone have any questions about that? I know we kind of had to stop early on Friday. Then let's take a quick peek at how they're implemented. So yes, you would create, yeah, that's just how to do prefix. But here's how the actual node class of a trie might be implemented. So we have something called node. It's going to store a single character. It's going to have to store some type of Boolean indicating whether it's a key or not. That's the equivalent of the purple versus white in our particular diagram. So the A has a true is key Boolean. Here you can see Y has a true is key Boolean. And then this is what's interesting. See how the next field, instead of being a singular node, instead of saying private node next, it's actually a whole map, which is what gives the trie the n-ary, pardon me, orientation. I'm so sorry. You can store as many children as you want here. So this is often how they'll do it with a map where you map from character to the actual memory location of the node representing that character. Yes, and then there you can see us sort of generating it. I think that's all I wanted to talk about with trie. Is there any other questions about trie or any of the trees we talked about on Friday before we dive into something new for today? Okay. Oh, are there any runtime differences? That's a good question. So remember that runtime is going to be dictated by how tall a given tree is. You can think of each level of a tree representing another recursion. So in this particular case, we're doing recursion through the trie based on the individual characters within a key. So it kind of depends on how long these strings are, how long any of your given keys are. And because there can be more children, you could get, say, 26 to the n nodes, which could cause you to have to do 26 to the n sort of journeys if you were to look at absolutely everything in the trie. But mostly the runtime is dictated on the height, and the height will be based on the average length of any given string, which is a totally different way of thinking about the runtime. If you think of n as the number of entries, you need to think about a separate variable, let's say, length L, and the length is going to dictate the length of any individual string. The average length of any individual string is what's actually going to dictate the runtime, because that's going to be the height or how far you have to recurse from the overall root down to a leaf. So the runtime for trie is usually a multivariable calculation because you need to keep in mind how many keys there are and also how many letters there are. Would a trie with all English language letters at the root node include a link from each letter to every other letter, and so on and so forth? It definitely depends on the situation. That's a great question. So yes, you could imagine, let's say we had a trie representing like the entire English dictionary. We definitely are going to have all 26 letters from the top node and probably the next few nodes. But it does depend on the entry set, how many children each of those things are going to have. So yes, this can be some of the most situation dependent runtimes. This is how Google does their autocomplete. And for context, they're running that type of search autocomplete on a distributed system across hundreds and thousands of machines distributed all across the world. So tries can be really powerful, but they can be very expensive. Okay, let's talk about a new ADT. So today and to Wednesday, we are going to be talking about something called a heap. as a data structure, but let's first talk about the ADT that the heap is most well known for implementing. So you may have heard of a priority queue in your intro classes. It is one of the built-in ADTs that exists in Java. A priority queue functions very similar to a regular queue, a queue without the priority in front of it. And what the priority queue does is as it takes in values, it orders them within the queue based on some type of priority. So it's not about the order in which you add things to the queue, it's about which value is determined via the compare to operators to determine first in priority. But let's talk about what that means. So let's imagine a scenario. Let's say you're managing a queue of fast food orders at a restaurant, and normally it's a first come, first serve basis, but suddenly you have some type of VIP or very busy person walk in. Let's say Anna Marie walks in, and you need to make sure that her food order gets served first. So a priority queue is something that does maintain order, but will also let order be superseded by a comparator, which comes in the implementation of the compare to method. So you have add, remove min, and peak min. There are other organizations to it. If you did Huffman coding in the intro series, that's what you are using a priority queue for. But you can also find priority queues in graph algorithms, sorting algorithms, printers, so on and so forth. So it actually does become a pretty popular ADT. Now, I've only talked about the capabilities, right? Like when I put something in, I get the highest or minimum priority out. Those are two actually just sides of the same coin. I think in the next slide, we talk about this. So you could have what we would refer to as either a min priority queue or a max priority queue. All that dictates that is the order of a comparator operator. So do you want the thing with the smallest value to get served up first, or you want something with the largest value to get served up first? In this particular class, we are only. Sorry, is there a question? Oh, okay. Let me know if you have a question. So in this particular class, we're going to be only talking about a min priority queue, just so that I don't have to reproduce things multiple times on the slides. But keep in mind that everything we talk about could be transformed to a max priority queue simply by changing the order of the operator. And so you can kind of start to think of this priority queue as maintaining a valid ordering within it at any given time, very similar to how binary search trees and AVL trees maintain that sort of binary search order amongst the nodes. We're going to have something similar here, where instead of left being less and right being right, we're actually going to maintain smaller than based on height levels. Sorry. Sorry, I'm trying not to cough into the mic, but I don't have a cough button, which is really annoying. So let's say we already know how to implement a priority queue. If we have a unsorted array, assuming we do not need to resize, adding something would always be constant, but removing min, we'd have to do a linear search to find the minimum value. Same thing if we're trying to peek, we'd have to search through the entire thing. If we maintained a sorted linked list, then maybe the thing at the front is this minimum value, so we can get that really quickly, but we're going to need an O of n time to maintain sorted order. The AVL tree, well, that could give us a way to find the minimum value pretty quickly, right? AVLs maintain a sorted order in terms of the binary search orders, but it takes us log n to add, log n to remove, and it is going to take us log n to peak, because where the smallest value is going to be starting at the overall root and going as far left as possible, which will be the height of the tree, which is log n. The point of what we're going to learn today is how do we implement this so that we then get a constant runtime specifically for the remove min and peak operations. So meet a new data structure that is going to implement the priority queue ADT. It's called the binary heap. So in a binary search tree, we organize data to find things quickly, going left or right to find things. Now, instead of finding an exact position for something in relative position to everything else, we just want to always be able to quickly serve up either the smallest or the fastest singular item. The other things can kind of be in some relative order that may lead us to finding the single smallest thing as quickly as possible, but we don't need to maintain as strict an ordering. So meet the heap. It looks a lot like a tree in that it is a binary structure. Each node has up to 2 children, and the heap invariant dictates that every node must be less than or equal to both of its children. So this is a valid heap in that 4 is less than 6 and 5, 6 is less than 8 and 373, 5 is less than 7. So the minimum value of the overall set, 4, sits at the very top. Now, this is also a valid heap for 5, 6, 7 because the minimum value 4 sits at the top, but you can start to see that degenerate organization coming through. And like I said, the height of the tree is almost always dictating our runtime. So this will likely give us a better runtime than this one. So I'm going to talk to you about how the heap tries to maintain its version of balance to keep the runtimes low. Great, great. Do we need more invariants? Sorry. So in order to avoid a degenerate tree, we are going to add in a second invariant, and this one is going to be something we refer to as completeness. So this is sort of the structure equivalent of balanced, but completeness actually turns out to be a less strict and somewhat easier to program invariant than balance. But what this means is that a complete tree has every single row totally complete from left to right with no gap, except for the very last row. So when we think about filling in our heap, we would start with the overall root 4. We would first fill in its left child, then we would fill in its right child. And then once that row is complete, the next place we would add a node is to the left of the leftmost child, then its right, then its neighbor's left, so on and so forth. So this tree down here is considered complete because the only gap exists to the right of 5, which is the rightmost possible space. So this is a complete tree. This is not a complete tree because we have this gap off of the 6 here, and we now have the 7 in place here. So we would not call this complete. For this to be complete, we'd have to move the 7 from being the 5's left child to being the 6's right child. Does anyone have any questions about the definition of this invariant of what completeness means? Okay, so here is the summary of our 3 invariants. Yes, complete is the best we can do to fill in the last row. The last row doesn't have to be fully complete, but all gaps have to be in the bottom row furthest to the right. So let's take a look at these trees. What about this tree, the 8, the 9, and the 10? Is this a valid heap? Throw it into the chat, valid or invalid. What do we think for this one? Is it a binary tree? Is it a heap? Is it a heap structure? Yes, I agree. Now remember, it's got to be binary. Love that. It's got to have every node is smaller than or equal to its children, which is true in this case, and this is a complete tree. Now let's take a look at this tree, the 1, 2, 3, 4, 5, 6, 7. Is this a valid binary heap? Go ahead, throw that into the chat. Love it. Yes, I agree, folks. This is valid. And you can actually see, like, this is the order in which we would fill things up. So 1 is the smallest value, it's at the top. We would then fill in 2, 3, 4, 5, 6, 7, and we're filling it top down, left to right. Okay, now let's look at this tree to the right here. Is this a valid heap or an invalid heap? Yes, I agree. And somebody even gave us a wonderful explanation. Invalid because it doesn't have a right node. Yes, I agree with Nola. There is a gap. There is actually a couple gaps. So one of the gaps is here, the right child of the two. So we can't have this row down here, this very last row, because there's a gap in the second to last row. So that's a problem. We also have another gap here, this left of 4. That's a gap. We can't have anything to the right of 4 if we haven't already filled that in. Does anybody see any other issues with this? I can't remember if there are. But otherwise looks okay. Any questions about valid heaps? Oh, we have a question. Go ahead if you just raised your hand.
Oh, hi. So I'm wondering if we have a like a binary tree, but we only have, for example, for the last row, we only have a left node, and then we just have one left node at the last row. So is that count for uh this heap structure?
So like, for example, if we had this structure here, the 1, 2, 3, and we just had the 4, but did not have the 5, the 6, the 7,
Yeah.
yes, that would still pass these invariants because the last row is allowed to have gaps, but the gaps must always be always to the furthest right. And that's because, we're not sure the order in which we're going to add things. And so maintaining a fully like no gapped tree might not work with how we're adding nodes in. But the point of the heap is that we're going to always fill it every row until the last row, but then we fill the last row from left to right.
All right, thank you.
Great question. Okay. Great. There we go. Okay. All right. So go ahead. Let's take a couple minutes here. Look at these and ask yourself, are these valid or invalid? And then we will come back together in a minute and I'll ask for somebody to explain to us why or why not these may be valid. Yeah, let's maybe start with this tree to the furthest left here. This tree with the overall root of 4. Is this a valid or invalid tree? And does anybody want to throw an explanation as to why into the chat? So for this tree here, is there invalid? Okay. Yes. Yes. Oh, yes, I agree. Yes. All of you so far are correct. So Nola says it's not complete, which is absolutely correct. We've got this gap here on 2. And then Ilse and then Elizabeth, you're totally right. We also have this, we've broken the heap invariant because 4 bigger than 3. So 4 is not allowed to be the overall root. Think if there we go. We've got a bunch of gaps in there, so that's a problem. Okay, what about this tree here with the overall root of 1? Anybody want to throw into the chat, is this a valid heap or not? Yes, I agree with Elizabeth. This is a big stick. It is not a tree. We could think of this as a degenerate. So this definitely breaks the completeness invariant as well. Anybody see any other out problems with this one? Yes, I agree with Nola. The 6 is supposed to be here. The 6 and the 7 are swapped. So great. We've got gaps and we've got invalid placement. Okay, then let's move on to our final heap here. This 4 is the overall root. Is this a valid or invalid tree? Any explanations? Valid. Yes, I think I agree with those wonderful folks in the chat here. 4 is the overall root because it's the smallest value. All of the children seem to be greater than their parents. And the only open gap is to the right of 5, which is exactly where gaps are allowed to be. Any other questions on this one? Okay. So actually, it turns out because of this completeness requirement, we actually even end up closer to a log n runtime because this is actually the strictest we can be in terms of maintaining the height of the tree by refusing to allow any gaps other than in the last level. It keeps our tree sort of as bushy as possible and thus as short as possible. So the runtime to traverse from the overall route down to the bottom is always going to be guaranteed to be theta of log n. Questions? Any questions come up, please feel free, raise your hand or throw them into the chat. Let's talk about some of the methods and how we actually fill up our binary heaps. So we know that one of the methods we need to implement is peak min. Peak min is a way to tell us what is the minimum value without actually removing it from the collection. And in a heap, that's great because we always know exactly where the minimum value is going to be. It's stored at overall root. So that is really great. That is going to give us a constant runtime to peak min. Just got to look at that top overall root node. Okay, what about remove min? So since the overall root is always going to be our minimum value, when we remove that thing, we are left with two nodes that now each don't have a parent. So we've got this really big gap and we've sort of split the tree down the middle and we need to find a new overall root. Now, you might be inclined to say pick between the 4 and the 7, maybe you pick the 4, but if we move 4 up, then we also have a problem finding parents for 5 and 8, and then we'd have to move 5 up, and then we'd have to have a problem finding parents for 11 and 13. So it turns out what is actually simpler implementation wise is to grab a node at the very, very bottom so that we remove the rightmost node, thus maintaining the completeness property first. And then we move that into the overall root because it doesn't have any existing children. So we maintain the structure invariant, but we break the heap invariant. This actually then kind of ends up being the opposite of the AVL tree, where with the AVL, we maintain the binary search property, but then break the structure invariant and rotate to make that right. In this case, we go first after maintaining the structure invariant, and then we're going to do something called percolating in order to repair the heap invariant. So what we're going to do is now that we have 13 at the overall root, the structure is still good, but we are going to do these node morphs where we replace 13 with its smallest child. This is called percolating down. You can kind of think of 13 as now having to travel down to the bottom of the tree. So 13 has 4 and 7 as its children. We're going to pick 4 because that's the smaller child, and we're going to swap it. And then we're going to ask, is 13 greater than its children? Yes, it is. So we're going to percolate it down with its smallest child. And then we're going to ask, is it finally in the right spot? Nope. So we have to do one more percolation down. So we are not changing pointers in this particular case. We're just morphing the nodes, which I know might sound like something we're not allowed to do. In this case, we're going to do it. And when we get to lecture on Wednesday, I'm going to show you why that's extra fancy, because in fact, we're going to mostly be implementing these with values in an array, not actual nodes. Now, this particular runtime, because all we have to do is find the rightmost node, and then it has at most the height of the tree to percolate down. This is going to give us a logarithmic runtime. And that completeness of the tree will keep the height of the keep the runtime small. There we go. Does anyone have any questions on how to remove min and then restore the structure of the heap? So are both remove min and percolate down log n? Yes, they are. So remove min actually will call a method percolate down. You do have to implement this actually in your P3, and you're going to want to create a separate percolate down method, which will be the thing that runs in log n time. So actually remove min's log n time comes from the percolate down behavior. Any other questions so far? Great question. But 13 right now is to the left of 11. Doesn't that break the binary search property? You're absolutely right. This is not a valid binary search tree, but I don't need a heap to be in binary search ordering. I only need it to be in heap ordering, which is a little more relaxed. In fact, you can kind of see over here, right? Like 7's left child is 10 and its right child is 9. Like that also doesn't follow BST. I guess the 10 doesn't. But that's okay because we just care about the relation between the levels. So actually, I don't care if the smaller value is to the left or the right. I just care that the larger values are the children of the smaller values. It's a little bit more relaxed order invariant. Good clarifying question. Okay, why don't you all do some practice? So draw the final tree when you would perform a remove min on this particular organization. And let's find out what the new overall route is going to be and which path it has to travel to get back into satisfying the completeness and heap invariance. So go ahead, take a couple minutes, perform a remove min on this example. No worries. Let's talk about this a little bit. So first of all, what is going to be our minimum value? What is the node that we are going to remove? Go ahead and spam that into the chat. What's the first thing we do? Yes, good job, everyone. I absolutely agree. Remember, we're going to take that 5 right at the top. It's going to be linked to overall route. You're absolutely correct. Now let's see if I have the animations. Now we have to replace it with something. What node is going to replace the 5? Which one are we going to pick from the bottom? Yes, absolutely. Yes, I gave it away a little bit there. But remember, we are ignoring the values. We're just maintaining the structure first and foremost. And what we're going to do is we're going to take the 18, which is the bottom level furthest to the right. We're going to grab that and we're going to swap that in with the 5. Okay, now we have a heap that looks like this. It's time to do our percolations. And so we're going to percolate 18 down. Which child am I going to swap 18 with? Yes, good job, everyone. I absolutely agree. Remember, in this case, this is kind of the only time we sort of look both left and right. And it doesn't matter where the smaller value is, whether it's left or right. We just want to make sure in order to maintain that min heap performance that we always swap with the smallest. So we're going to swap 18 with 9. Now, do we need to keep swapping? If so, which value are we going to swap the 18 with? What happens next? Yes, Absolutely, everyone. I agree. We're going to swap 18 with 11. That's the smaller of the two children between 13. Okay, what about now? Do we need to keep percolating? Am I going to swap with any further children at this point? So what children? Yes, good job. Actually, now 18, it didn't even have to percolate all the way down to the final row. It kind of comes to its final resting place at the second to last row, but you can see it followed that one path all the way through. So we've got that sort of worst case scenario logarithmic time. Any questions on this problem or how we got this orientation of heap? Yes, so this is just a reminder that when we are doing our swaps, we need to make sure we always swap with the smallest child, not just any child, because that's how we maintain that heap invariant. So great question, Kristen. Yes, so the percolation is the logarithmic runtime, but every time you call remove min, essentially what remove min is going to look like is it's going to be a call to grab the value at the very top overall root and then call percolate down after you move the bottom value in. So the logarithmic runtime of remove min comes from the percolation action, which is always going to be triggered by some type of remove min. So you can think of percolate down as always being called within a remove min structure here. So technically, yes, they're both log n, but the log n for remove min comes from the percolation. So let's talk about maybe the opposite direction then. Let's say we need to add a value. So very similar to how we removed min, when we add a value, we are going to insert the node to first maintain the completeness, and then we're going to perform a percolate up in order to let that value sort of float up to wherever it belongs. So we will need to maintain some type of pointer so we always know where is the next available spot, like where is the next place that any node needs to go in order to maintain completeness. In this case, remember, it is always the leftmost space in the second to last tree, because that's where you're going to put, or second to last row, because that's where you're going to put your child. So no matter what we're adding to this tree, we know that a node needs to go here to the left of 8. Let's say we added in the value 3. Now we've added it where it will maintain the completeness of the tree, but 3 certainly breaks the heap invariant. So very similar to how we percolated down, now we are just going to do the same type of logic where we're going to mutate those nodes on our way up the tree. So the first thing we're going to do is ask ourselves, is 3 a smaller value than 8? Since it is, we're going to swap those values. Now we're going to look up again and we're going to say, is 3 a smaller value than 4? Yes, it is. So we're going to swap 3 and 4. Then we're going to ask ourselves, is 3 a smaller value than 2? Well, it's not. So now 3 has sort of appropriately floated up to the place in the heap where it belongs. And we've only had to mutate these 3 nodes in order to get there. So a worst case runtime is going to be a log n runtime, and that's if the new value that you add is the new smallest value in the tree. So we would get a full log n runtime if, say, the value we added in was 1 and needed it to percolate all the way up to 2. But in general, you'll kind of get a little bit better performance with add because it's less statistically likely that every single time you add an item, that will be the new smallest value. Unless, of course, you're adding everything into the heap in reverse order. Then every time you add a new node, it'll have to percolate the entire height of the tree up. Let's see, is it possible to place the 3 where it needs to be on the way down, or you can only percolate after placing it first? So I have been sort of saying, oh, look at my parent, and oh, find where this thing belongs, in the next available spot. But if you think about it, knowing about the structure of other nodes within a tree is actually really difficult to do. So if we were going to do this in actual nodes, we would be having to do an almost linear search of the tree regularly to find your parent, or we'd have to have nodes that have like reverse pointers or something like that. Because we don't have that, it is much easier to maintain the structure first and then just change the values. So we're always going to maintain the structure first and then just do these mutations because they're going to be cheaper. And like I said, foreshadowing, we're eventually going to implement this not with nodes, but with an array. So these types of percolations are going to be performed by just swapping within an array. But we'll get into that in future slides. So why is the count for swaps log n? So in this particular case, it's like log n minus 1. But we have a log n runtime because it's a binary tree that is perfectly balanced. And so what that means is that the height of the tree, this height, meaning 1, 2, 3, that comes from the fact that this is a perfectly balanced tree, meaning half of its nodes are to the left of the overall root, half of its nodes are to the right of the overall root. So we maintain that logarithmic height. So anytime you travel a singular path through the tree, that counts as the log n time. And that's all because first and foremost, we're maintaining the structure. What's the time complexity for finding the bottom level rightmost node in delete? That is a great question. So what we could do is if we were doing this with nodes, we could run a traversal and run until we just find the leftmost open value. But that could end up being a worst case linear search through the tree if we were actually using recursion to travel through the nodes. But I'm going to show you a really clever optimization so we don't have to do it that way, where we actually can find a way to reduce that linear search for the next available spot. And we're going to do it with an array. Yes, this is not a BSD. We have a slightly more relaxed ordering property. So, that's why, for example, this 4 and 5 here swapped, not a problem. This 5 can be to the left of 3. It's not a BSD. If the tree is not balanced, is it still log n? So this tree is what we would call complete instead of balanced. And actually completeness by definition will remain closer to logarithmic time than even balanced trees will. So by definition, we've always maintained the structure first and then done the order swapping. So a heap will maintain the most close to log n height of any of the trees we've seen so far, because we always select for optimizing to maintain the structure before maintaining the ordering property. Okay, what time is it? Is it 1:20? Sorry, I should have my phone out here. Oh shoot, I'm sorry. I did not realize it was 4:22. I kept you a little long. There is a practice here and some really delightful animations. Maybe you want to give that a try in your own time. Come back on Wednesday. We're going to do some practice with our warm-up, and we're going to talk about how you actually implement a heap where you don't use any nodes at all. I'm happy to stick around and answer any more questions, but thanks so much everyone for being here in the meantime. With using completeness in the invariant AVL benefits performance? Ooh, that's a really interesting question. So we can't do completeness in the AVL space because that strict binary search property, we need to sometimes leave gaps here and there because the left and right don't function the same in terms of the ordering. So we can't just necessarily fill up every single level, and we have to do those rotations. And that's because BST is just stricter than heap. Great. Thanks so much, everyone. Thank you. Thanks for being here. Thanks for your patience as I cough into the mic. I appreciate all of you. Thank you. I really hope I feel better. I think I probably will in a couple days. Thanks so much, everyone. Happy midterm studying, and hopefully you get plenty of help from the TAs and office hours.